Okay, this video is going to go over inductors. So inductors are just like masses, but for the electrical world. They're described by a flow, a current in this case, I, and have an inductance L instead of a mass. Now their symbol looks like it's a coil essentially, where we have our L here for our inductance, and then we have our current flowing through it, and I use the double arrows here to represent that flow. And then these two circles on the ends of it, that's these terminals. And I sometimes use those to show connections to outside the system or outside the element into the environment. And then the plus and minuses here are kind of like our R1s and R2s for the mechanical systems. They represent, our voltage direction, and a positive current will flow from positive to negative for these. So the equation of motion in quotes here, the equivalent equation of motion in Newton's second law for an inductor would be L I dot is equal to V. So V is our sum of our forces, that's our net force, and then I dot, that's like acceleration, but for current instead of velocity. Now, for inductors in series, if you have multiple of them in series together, all you need to do is sum up those individual inductance values together and you'll get an equivalent total or equivalent inductance value. And then if inductors are in parallel, what you do is it's similar to what you would do for resistances in parallel. You sum the one over those inductances and then take the inverse of that. And now, just like with masses, inductors store something like kinetic energy. So I'm going to put kinetic energy in quotes here, and that is equal to 1/2 Li squared for a linear inductor. And that is going to cover inductors.